In this lesson, we're going to look at the chemistry of buffers. So this is section 5.2 from your workbook, and we've got 4 goals for this section. We're going to define what a buffer is and describe how to make a buffer. We're going to explain how buffers work to resist changes in pH. We're going to go back to our equilibrium equations for that. And then finally, we're going to discuss some applications of buffers. So first off, the definition of a buffer. Buffers are things that resist changes in pH. So we add a buffer to a solution so that if we add an acid or add a base, the buffer will resist against that change. It will stop it from becoming acidic or stop it from becoming a base when small amounts of the acid or base are added. So to understand a buffer, we have to understand equilibrium. So here's the first kind of step for creating a buffer. We're going to look at weak acid equilibrium and the common acid effect. So our example here says, write an equilibrium reaction for a 1 molar acetic acid solution. So when I mix acetic acid with water, I get the acetate ion, that's the conjugate base of acetic acid, and I get hydronium ion. Okay, and I can write out an ice table if I want. I don't actually need one for this particular application. So if you take a look, we've got this acetic acid solution in equilibrium with the acetate ion. If I increase the amount of that acetate ion, what is that going to do to equilibrium? Well, it's going to shift equilibrium to the left. If I shift equilibrium to the left, that's going to increase the amount of acetic acid and decrease the amount of the hydronium ion, which is what's making that solution acidic. So this is actually how we prepare a buffer. So if we add sodium acetate, this is how we can get all of this to happen. We're adding sodium ions, we're also adding the acetate ions. So this is how we can actually get that increase in the acetate without adding acetic acid. So you'll notice kind of the takeaways from this is that my concentration of the acetate ion will increase. That shifts equilibrium to the left. Shifting equilibrium to the left will raise the concentration of acetic acid. However, it'll lower the concentration of the hydronium ion, which is making that solution acidic. So kind of the result of this is that when we have this equilibrium between the acetic acid and the acetate ion, when we've added the salt of the conjugate base there, that sodium acetate, what we've done is we have made it so that we've got an equilibrium where the concentration of hydronium is very low. We've got the concentration of acetic acid fairly high, concentration of that acetate ion just a little bit lower than the concentration of the acetic acid, but we've really lowered the concentration of hydronium. So one thing to note with this is that they don't actually neutralize. We have an equilibrium between the acid and the conjugate base, and this is how we're preparing our buffer solution. So there are 2 types of buffer solutions. The first one is the weak acid and a salt of its conjugate base, which is the first example that we just went through. So for example here with the acetic acid, that's the weak acid. We know that the acetate ion, CH3COO-, is the conjugate base. And a salt of the conjugate base, we can just combine that acetate ion with any of our spectator ions. And I've chosen to use sodium in this particular case because it's readily available and usually pretty cheap. But we could have gone with a potassium acetate, it would have worked as well, okay? So by doing that, what we're doing is we're moving equilibrium, trying to equilibrium is going to move to try and replace those hydrogen ions. And if we've put that buffer solution in with a weak base, the hydroxide ions will then combine with those to make water. So it works both ways, not just to buffer acidic solutions, but to buffer basic solutions as well. A second way of creating a buffer is to use a weak base and the salt of its conjugate acid. So a weak base, here's an example, NH3, my ammonia, and the conjugate acid is the ammonium, NH4+. So if I want to create a salt of the conjugate acid of that weak base, all I'm going to have to do is mix it with another spectator ion. So I've chosen to go with Cl. We could also add any of those conjugate bases of the strong acids. One thing to note is that buffer solutions cannot be prepared with strong acids or bases because there's no equilibrium there. Those reactions go all the way to completion, so we can't create a buffer solution just like that. So here's how a buffer works to minimize pH changes. Again, I've used my acetate and acetic acid as the example here. So when I have this equilibrium, the question is, what happens when hydrochloric acid is added? When the hydrochloric acid is added, what we're actually doing is we're increasing the concentration of hydronium. So that's going to shift equilibrium to the left. Shifting equilibrium left will increase the concentration of the acetic acid, the CH3COOH. It will decrease the concentration of the acetate ion, and it will decrease the concentration of the hydronium ion. So adding HCl, we're going to decrease the concentration of the hydronium ion, resisting that change in pH. So if I take a look at the concentration of H3O plus over time, you can see that the H3O plus is kind of stable at the beginning. It peaks there when I'm adding the hydrochloric acid because it takes some time for that reaction to occur. But then we're going down, down, down until we have just this really small net increase in the concentration of hydronium, and it's because of that equilibrium. With pH, if you'll remember, pH is inversely related to the concentration of hydronium. So when I have added that acid, the pH actually dips, and then it's going to go back up almost to where it was before. It'll never get quite to exactly where it was before because of the way the equilibrium works, but it'll get close. So here's another example of how the buffers work to minimize pH changes. This time we're going to try it with a base. So what happens when sodium hydroxide is added? Well, that hydroxide from the sodium hydroxide will neutralize the H3O plus. They'll mix together in a neutralization reaction and form water. So that's going to decrease the concentration of hydronium. That's going to shift equilibrium to the right. And if we shift equilibrium to the right, we're going to get increases in hydronium and acetate ions and a decrease in the acetic acid concentration. Again, it's going to resist that change. So here's where we have that concentration of hydronium over time. You can see that we have a sharp decrease in hydronium when I first add the strong base. But then as equilibrium shifts to the right and restores that concentration of hydronium, we're going to go back almost to normal. With pH here, pH is showing how basic it is. So when we add that strong base, we're going to get a higher pH. And then we're going to be going right back almost to where we were before with normal. So the last kind of section that we have here is how can we apply this? Why are buffer solutions so useful? And one of the reasons why buffer solutions are so useful is in the food industry and in pharmaceuticals for that matter. In the food industry, sodium, potassium, and calcium additives often cause a buffering effect. So sodium citrate is an example, calcium citrate, potassium citrate are all substances that are used in the food industry to resist changes in pH. And we might do that to prevent discoloration of fruit. So I've got apple slices at McDonald's, for example. If you read the ingredients, it's not just apples. They've got an additive in there. It's a food safe additive that will stop the apples from going brown. They're also used to maintain a constant acidity of jams. If your jam gets too acidic, it won't gel properly. So you need to maintain a constant acidity. And then also it's regulating acidity of carbonated drinks. When we add that carbon dioxide, the drink will actually get quite acidic. And so we want to make sure that that's regulated in a very precise manner. Another application of buffers is looking at how bad acid rain is going to affect a lake. So if we have a lake with a limestone bottom, they're actually naturally protected from acid rain because they will produce a natural buffer solution. So if we have an area that's affected by acid rain, we can look at what type of bottom it has in the lake. If it's something with limestone, then probably that lake will be okay. However, if it's granite, like the Great Lakes the Canadian Shield Lakes in Canada, that doesn't have the same buffering effect. And so the fish population will be much more affected by acid rain in that region. Lastly, another application of buffers is in blood chemistry. And if you're taking anatomy and physiology or have taken anatomy and physiology, we've talked a little bit about blood chemistry. There is a buffering system in your blood that has to do with carbonic acid that's formed when carbon dioxide mixes with the water in your blood plasma. And that buffering system goes with a bicarbonate ion. And so that helps to buffer the blood and keep the blood pH very, very regulated. So there's another application of the buffers. That concludes our lesson on buffers today. And there's a number of different topics that you're able to choose for your final assessment in this unit as well. So if any of this stuff interests you, I encourage you to dive in and check it out. Thanks for watching.